We're going to be using two different cars in order to test collision. So for the first part, we're going to be using the same carts with both the same masses, and then we're going to be testing elastic collision. For the second part, we're going to be testing inelastic collision with the same masses. For the third part, we're going to be testing elastic collision with one at different mass, and then for the fourth part, we're going to be testing inelastic collision with different masses. Dip us in the real world, see how different size cars can affect if they collide into each other.
Lab will be using the following materials. First of all, we're going to be using two wireless smart cards, a red one and a blue one. Each of them have a magnet inside of them, and this is going to help us do elastic and inelastic collision. And then we're also going to be using a track in which we're going to locate the wireless smart cards. And then we're going to be using this mass, which is 250 grams, for us to measure the elastic collision and the inelastic collision with different mass. And the trap has a magnet. We're going to be using also the interface and our system as usual.
Part of our experiment, we're going to do elastic collision with both masses the same. And what we're going to do is that we're going to put these two cards with the same mass, and we're going to run the system to start recording, and then we're going to collide these two cards and see what happens. The second part, which is an elastic collision with the same masses, we're going to do is that we're going to collide these two cards with one magnet opposing the other card, and we're going to see what happens. Third part of the experiment, and now we're going to do elastic collision with different masses. So what we're going to do is that we're going to put the cars with the magnets looking at each other, and then we're going to collide them and see what happens. Fourth part of our experiment, and this is going to be about an elastic collision with different masses. So what we're going to do is that we're going to put one card with the magnets viewing at the back of the other card, and this card is going to have a mass of 250 grams. And we're going to collide them and see what happens.
With elastic collision and with the same maths of the cards, and then this is the graph that we got. So this is the position graph. You can see we let it run for a little bit for it to start nicely, and this is where they crashed right here, and this is them continuing their journey. And then this is the momentum graph, and this is the kinetic graph. Graph with inelastic collision and with the same weight. So this is right here is the position graph. Right here in the middle is where they crashed, and then they stay together most of the time right here. This is the momentum graph, and this is the kinetic graph. Part we did elastic collision with different mass. So the blue car weighed more, and then this is how the graph came out. So their position was this. This is where they collided right here. And then this was their momentum change and their kinetic change. Inelastic collision with the different weights, and this is how the graph came out. So for the position graph, you can see right here, this is where they collided, and then this is the before and this is the after that we got. This is the momentum graph, and this is the kinetic graph.
This is the data that we collected from the inelastic and elastic collisions. So first we have our same weight. We just used a blue and red car, and this is our momentum and our kinetic energy before and after the crash. So first in our blue car, we got 0.1 in momentum, 0.02 in kinetic energy for the blue car, and then for the red car, we got negative 0.09 and 0.02 for the kinetic energy before, and then the totals for that was 0.01 and 0.04. And then after the collision, we got negative 0.08 and 0.02 for the blue car, and then for the red car we got 0.09, and 0.02, giving us the totals of 0.01 and 0.04. And then for our inelastic collision, our before was negative 0.01 and 6.28 times 10 to the negative fifth. And for our red cart, we had negative 0.16 and 0.06. And then after the collision, we had negative 0.03 and 0, and 0.02 and 0. And our totals were negative 0.01 and 0. And then for going back to our elastic collision, but this time we added a weight to one of our carts. So for the blue cart, we got 0.25 and 0.07 before the collision. And then for the red cart, we got negative 0.13 and 0.04. And our totals were 0.12 and 0.11. And then after the collision, we got negative 0.1 and 0.01. And then for our red cart, we got 0.15 and 0.06, and our totals of 0.05 and 0.07. Going back to our inelastic collision before, we had negative 0.6 in momentum and 0 in kinetic energy, and negative 0.19 and 0.09. And our totals were negative 0.25 and 0.09, and that was before our collision in the inelastic collision. And finally, in our last trial, we got our after collision in the inelastic collision, and negative 0.13 and 0.02 as our momentum and kinetic energy, and 0.03 and 0 as our after. And then our totals were negative 0.1 and 0.02. And then using that, we were able to get our percent difference having the same weight and different weight in our momentum and kinetic energy. So in our elastic collision, using our totals, we got 0% and 0% for momentum and kinetic energy, which is really good, meaning that the momentum held on in both carts after and before the collision. And for the same weight in our inelastic collision, we got 94% and 100% for our momentum and kinetic energy, which is very high, meaning that the momentum didn't stick through. And for our different weight, when we added the weight for our elastic collision, we got 58% and 36% as our momentum and kinetic energy. And finally, for our inelastic collision with this different weight, we got 60% in the momentum and 77% in the kinetic energy.
As far as our conclusion, we'll be answering some questions regarding our experiment with two different scientists. And our first scientist is Alexandra. And my first question to you is, how did you produce a relatively perfect elastic collisions between the two carts?
We produced a relatively perfect collision by making sure that the forces that we pushed the carts with were equal in the amount we used.
My second question is, how did you produce a relatively perfect inelastic collision between the two carts?
To perform the inelastic collision, we had to make sure that one of the forces that we used was a little bit less than the cart with more force, so they would be able to stick.
My other question to you is, were there other options to achieve your purpose? Other options to achieve your purposes to produce a relatively perfect elastic and inelastic collision?
I'm pretty sure there was different options we could have used, but these were the ones we found most easier.
Question to you is, what criteria are you using to determine the conservation of each quantity?
Initial and final values that we got from momentum and kinetic energy from our graphs that we produced, and system boundaries, whether it was a closed system or open system, meaning that there were other factors playing into when we were pushing the carts.
Is when we say something is conserved, the percent difference is near or far from zero. Why?
In our tests, we had some that were very near zero, and some that were exactly zero, and some that were very close to 100. The thing that changes it is the amount of force that we use when we push the carts from one side to the other. So that changes the variables.
The second question is, the theory says that momentum is conserved in both cases. Does your data support that argument?
In some cases, yes. When we had the carts of the same weight, the momentum and kinetic energy remained very near zero and gave us a percent difference of 0%. And then in other cases, when we had the same weight of inelastic collision, that gave us a closer percent difference to 100%, meaning that it did not stick through. And the same results gave us for the inelastic with different weight and elastic with different weight. Those were near 50%, 36%, and 60%. So a lot farther from 100, but still closer to 100.
Why or why not?
The amount of force that we put into each cart changes the variable and the weight. So sometimes the carts didn't stick, so that's what changed the momentum from it.
What do you think affects your experiment?
Force and weight.
In which cases can you say that kinetic energy is conserved and in which is not?
In the elastic collision, when we had the same weight for both carts, when there was no additional weight, we were able to keep the same momentum and kinetic energy before and after the collision. But for the inelastic collision with the same weight, we weren't able to do any of that and actually gave us the percent difference of 94% and 100%. When it came to the elastic collision and the inelastic collision that had the different weight, the elastic collision gave us a 58% and a 36% chance. So that's less than 100% and closer to 0%, but still that was a big difference. And for the inelastic collision, it gave us 60% and 77%.
What criteria are you using to determine the conservation of each quantity?
Initial and final values that we got from momentum and kinetic energy from our graphs that we produced, and system boundaries, whether it was a closed system or open system, meaning that there were other factors playing into when we were pushing the carts.
Procedure and with the setup of the experiment.
I helped make the tables and played one of the scientists.
The system, and I helped testing the procedures. I was also one of the scientists.
With some of the setup with the experiments, recording some of the frames of this video, editing it, and I was the journalist.